Hello, this is my lab 4 for Physics 2212. This lab is based on circuits. Introduction. The aim of this lab. By using the principles of energy conservation and current conservation, predict the behavior of circuits containing resistors in series and parallel, then use multimeters to measure the actual values of conventional current and potential differences and examine the behavior of ohmic resistors and capacitors. Some key ideas: energy conservation based on the loop rule, current conservation, that is charge conservation plus definition of steady state, the node rule, the Ohm's law, which is V is equal to IR, capacitance and resistance. Assumptions of the models. The experiment was done online using a Phys simulation, so the model is considered to be ideal and the only source of error is human error. Some assumptions: resistance is negligible in the ammeter and the wires, and the EMF is equal to V cap plus V resistors. The results: for the series circuit, the change in potential difference is 0 volts, and in the RC circuit, the experimental RC was 5.99 seconds and the calculated one was 6 seconds. Part 1 was series circuits. I predicted that I1 was equal to I2 based on the node rule, and this is confirmed by a calculation that's seen below. The total resistance was 47 plus 100, which is equal to 147 ohms, and I is equal to V over R, which comes to 0.0204 amperes, or negative 0.204 amperes if the ammeter is connected backwards. Replacing the ammeter with a voltmeter, the voltage remains the same to 3.00 volts, and the current is equal to 0 since this is an open circuit, so no current actually flows through, and the potential difference still remains constant. We then calculated the round trip potential as seen below, which is basically the potential difference across different sections. The potential difference across the wires was said to be 0, and across the two resistors is negative 0.96 volts and negative 2.04 volts. If we take the sum, we get delta V is equal to 0, which is as expected. Here I have graphed the potential difference across the entire circuit. So as you can see, there's a total EMF of 3 volts. This is the maximum potential due to the batteries. It's achieved at point B. From C to D, there's a potential drop due to the resistor, which is equal to 0.96 volts. From part E to F, there is twice as large of a drop of approximately 2.04 volts as calculated previously. This is because the resistor now has twice as large the resistance. The ammeter reading does not change due to the voltmeter because the resistance is very high, which means that no current passes through the voltmeter and the current remains the same overall. The current increases from 0.02 amperes to 0.06 amperes. This is the result of the current coming into contact with less resistance, which is being split between the 100 ohm resistor and the ammeter. According to the formula, I is equal to V over R, when resistance decreases, the current increases. The results of the series circuit: for the part A, we got resistance to be 48 ohms, which is pretty close to 47. For part B, we got 102 ohms. This is slightly higher due to the extreme significant values. The resistance of the wire and the ammeter is both 0 ohms as expected. Part 2, the RC circuit. I used a 10 ohm bulb, a 20 ohm bulb, a 9 volt battery, and one 200 microfarad capacitor. The observation was that the 10 ohm bulb starts off very bright and then progressively decreases over time as the battery is connected, and the current starts off high and then decreases to 0. Next, based on the capacitor, the 10 ohm bulb lights up once again and then progressively decreases over time again as the battery is disconnected, and the current starts off high and then once again decreases to 0. The time it takes for it to discharge for the 10 ohm bulb is 8.23 seconds, and for the 20 ohm bulb is twice as long, 16.4 seconds. On the left is a data table, and on the right is a graph that has been plotted. The slope of the curve is negative 1 over RC, which gives us RC to be 5.99 seconds. This is very close to the calculated RC, which is equal to resistance to capacitance, which is 13 to 0.2, which is 6 seconds. Now answering the discussion questions. What if we were to do this lab in real life and use an actual ammeter instead of the ideal simulated ammeter? What would be the difference between the real ammeter and how would it affect the circuits that we had hooked it up to? In an ideal ammeter, we assume that it has 0 to negligible resistance, which means it lets all the current pass through and there's no decrease in current due to the ammeter. However, if you use an actual ammeter, there would be a current drop that would be seen, and this would affect the values that we had calculated. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? If we were to repeat this experiment in real life using a real battery, the capacitor would take longer, or it would take more time to reach full charge. This is because the wires would have some resistance in them. However, in the Phys simulation, the wires are said to have no resistance, and therefore the capacitor charges up immediately.